All right, here is the fill in the blanks for the crude birth rate formula that we did yesterday, so you can have it on video. Remember, and I want to say this on the video, you are responsible for a certain amount of formulas. Growth rate, natural rate, crude birth rate is one of them. Crude death rate, crude growth rate. Doesn't matter the way the question is approached. You will be given a year, you will be given a total population, and you have to calculate the crude birth rate. They could also give you the crude birth rate, and you know, the formula works in all ways. So know that knowing the formula, you will be responsible for some version of that formula. And sometimes the question is not calculate the crude birth rate, it's calculate the year the population will double. Like this question, okay? No, that wasn't this question. What am I talking about? Yes. I'm not talking about doubling time. Redo. We're talking about crude birth rate, okay? Now we're going to talk about doubling time, which is calculated with the rule of 70. You could use the rule of 70 to calculate the doubling time, which is by definition how long it takes a population to double in size, or you could use the formula to calculate the growth rate. In that case, they would have to give you the doubling time. Whatever is given, it's 70 over that number. If they give you the rate, it's 70 over the rate to calculate the doubling time. If they give you the doubling time, it's 70 over the doubling time to calculate the rate. Okay? This is where the year could kick in. So in this particular question, here are all the answers so that you can have it on video. This is what we did yesterday. You will need to calculate the growth rate, the doubling time, in order to predict how long it will take the population to double. And the question could go as far as to ask you, what year is that? Okay? Any questions? Okay, you'll have time to fill this in if you're missing. Yeah. Here's the other formula question. So you could have it on video as well. In this case, we were calculating the rate instead of the, and you can add here in your notes, rate is equal to 70 over 56, which this is the given, which is the doubling time, okay? Well, okay, you know what I'm saying. I'm just going to put T. All right, and also here, in case you needed this formula here is 2010, which is what's given, plus the doubling time, which is 54, and that's how we got that answer, because I know that wasn't in your notes. Like, I gave you all formulas, and I left that formula out. So in case you need to know what calculations took place, that's the final part of the calculation. All right, we already did this. We had done this the day before. That's in the other video. This is in the other video. This was not. This is what we tried to do yesterday, which was a hot mess. I'm just going to release all of the blocks so you could fill them in case you had any mistakes. But I am going to go over this because I did not do this with period C. So a population can't grow indefinitely because there's always going to be factors that influence growth rates. Okay? That's what the rest of the notes are. What are factors that influence growth rates? We know that birth plus immigration minus death plus emigration gives you the perfect calculation. But what influences birth? What influences death? What influences migration patterns? That's what we're going to be talking about. We're also going to be talking about resource availability, resource that stops populations from growing, and how economy has a factor in that, education has a factor in that, all of those things. This is what we call biotic potential. If you don't have any limits in your environment, you don't have limits of resources, any kind of resistance for reproduction, populations will grow and they'll thrive, okay? But there's always, in reality, some kind of limit, and that's what's called the carrying capacity. The carrying capacity is the limits, and populations will always fluctuate around that. If there's resource availability, populations grow. Once you hit the carrying capacity, populations should either stabilize, which is stay on or around the carrying capacity. If they exceed, and I'm going to talk about that in a minute, other things will happen to the population. So environmental resistance limits population growth, and that's really measured as the carrying capacity. So I know you know what this definition was, but we didn't talk about this yesterday. When you see a carrying capacity sign, you're talking about the maximum amount of anything, species, weight, food, whatever that's available. That's what a carrying capacity is. It's hard to measure human population carrying capacity because we obtain all our resources as needed. But in reality, think of water. If you live in a state where water is a struggling resource, the population is going to struggle because water is a necessity for life, okay? Animals go through this all the time. So what is K? Carrying capacity, okay? Now, or environmental resistance is this shaded area. But K is your carrying capacity. So write that down because I don't think I have it here. Whoops. Now, this is what we talked about before, which is your biotic potential, no environmental resistance, unrealistic. It's kind of like a fundamental niche, right? Same type of curve. You don't have any influence that would negatively impact populations from thriving. There was a time that all these curves appeared on the AP exam and you had to actually name the curve, which is ridiculous. But I think the important thing is to be able to look at a curve and think of a scenario that could have caused this curve. So let's go with this. Tell me what you think erupt. Describe an erupt example. I'm not standing in the center of the room, but I did talk louder, I did pause, and I did say the logical question would be, right? Okay, who could do that? So easy. I'll pause. This is an example of an influx of immigration into a specific country or city. Yes. What else? Are you going to give us something different? I can't hear you. Formation of an island. No. And I have an entire slide on that I'm going to go over next. But I'm asking you, describe erupt. Give me a scenario that would describe what is happening here to the population. You know what? You've never heard of baby boom? The soldiers came home from war. Right? Happiness right there. Boom. Okay. What about this? Were you going to give me something, Nick? What? I love it. A species of animal, and they had reproductive environmental influences for the highest rate of reproduction, and I accept. A new fertility drug, I don't know. Anything. What about this? Just describe it. What's happening? What would cause up and down cycles of population? People that have two homes, they live in this home for the summer, so climate influence is definitely a cyclic type of pattern of population, okay? How about stable? Everyday, perfect scenario, I would say. If you have a stable population growth, you're saying that that environment has the necessary resources for survival and no impacts for decline, because decline is the hard part. And then obviously you can come up with anything for irregular. All right. So if there's no environmental resistance, you have what's called intrinsic growth rate. It is a rate with no environmental resistance, which is not even realistic. Again, just like fundamental niche, right? No resistance. That is our J-shaped curve, and J-shaped curves, by definition, describe exponential growth. This is the growth the population has been experiencing since the baby boom. Around the 50s, our population has been growing exponentially as a whole. It's not just less developed countries, it's all countries as a whole are experiencing exponential growth. And it is believed that it will continue until about 2050 is the predictor of most population researchers. Logistic growth describes growth where there is environmental resistance. Bless you. I don't know why that word wasn't covered. But this is what we call stable growth. It's stable because populations will grow, and once they reach the limits of their environment, they should stabilize. That's called logistic growth. And the limits are, like I said before, the carrying capacity. Now, let's say I gave you this question. I'm going to jump right here, and then I'll go back so you can finish writing. If I gave you this graph right here, okay, where do you think the carrying capacity line would be for the irregular curve? Huh? So where? So I'm gonna take this pen and I'm gonna say, you said in the middle. So if I go from here to here, you're saying it's here? Who agrees? So if I keep going, does that look about right? So look at this right here. Look how long this population is thriving above the carrying capacity. Does that seem logical? Not only did it survive, it actually recovers. How can you recover if you're above the carrying capacity? It's impossible. So I would not give you a question this hard, but I want you to know that if you are asked to draw an imaginary carrying capacity line, you have to go wherever, you don't go where the peak is, but you go where you see that population struggle to survive once they pass this line, which means you could pass it for a little while, but then you're always going to drop back down. Does that make sense? And again, I wouldn't give you such a hard line. It would be more along the lines of this, right? Yeah? And again, this would not be a case. You should not have a declining population below the carrying capacity. If you exceed the carrying capacity, you can have a rapid decline, but eventually you should see some kind of stabilizing curve, okay? Because this is what happens when you stay below or on the carrying capacity. If you exceed, the population will decline, but there should be a recovery phase. If resources can regenerate. If we're talking about an unlimited resource and the population lost that resource, the population cannot regenerate. Now, we talked about this yesterday, yes? Okay. I'm just going to uncover in case anybody missed those covers, but resources, predation, competition, disease are all factors that can influence a population growth or decline, because if you have unlimited resources, populations grow, yes. If you have a good predator-prey relationships, populations thrive also. And then I added war here, guys. I didn't talk about this yesterday. That should have been there. War can definitely be a density-independent limiting factor, as I'm sure you know. It could completely change population sizes. So please add that. We did this slide yesterday too. I want to put it in the video. The majority of the conversation we're going to have from here on out is about world populations. So this is developing countries versus developed countries, and we filled in these blanks yesterday, but I mean, clearly you're talking about industrial economies versus agricultural economies, education versus lack of education, and those are the key factors that are going to determine birth rates, death rates, growth rates. Any questions? Okay. What's the current world population? 8+ billion, yes? And most populated countries? China, India, US, okay? And I went to the clock. I'll go to the clock so you could see it, because that's what I should do. World. That's why I thought it was 8.2. It's 8.183. if we look at, see if I could look at years. Well, I'll show you. Births today, deaths, I mean, it's calculating. Births this year. I could use any of these numbers to come up with some formula, but I wanted to show you, again, like we talked about yesterday, how much there is a difference between size and density. Because if you look at India's size in comparison to China, and India and China are constantly fluctuating with the most populated countries. But I also want to show you let me see if I could get a population growth. I mean, here, let's just look at this. So this honestly should be in your notes, and that's why I'm showing it to you in a video. So this shows population from 1790 until today. And as you see, look, stable, stable, stable. We started to see some growth, but right about here, it went, I mean, it's grow, 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 but it like from 1950 to 2000, it doubled in size. It never did that before. 1950 to 2000, we practically doubled in size, okay? 2010. The growth is steady and then experience exponential growth, and we're going to talk about that growth in a minute. Or maybe not today, but eventually. All right, so, oh, here it is. I know I had it in there. So 2 billion people in 1927, 4 billion people in 1960, and then 2024, 8 billion. Look at this growth here. Okay, why? That's what we're going to spend the rest of the time talking about. So there's 3 main reasons for growth. What are they? Yes, resource availability, but it's really this resource. And the reason we had this resource was why? We went from living in the forest, going from place to place, right, which are called nomads and hunter-gatherers, to what? Who were the successful, the first group of success, which became a revolution? Who? Farming. Agriculture. Because the history of humans makes sense. Going from place to place, trying to find resources, living without shelter, okay? And by shelter, I mean a home, definitely impacted growth rates significantly. When you settled and you started to grow food, that was one of the key factors. And that's completely directly linked to expanding habitat. So you go from farms to towns to cities, you see the growth, right? Massive growth. And then one key important thing led to exponential growth. Which is what? Well, I heard it. I heard somebody say it. What about disease? Would disease cause expanding exponential growth? Resistance to disease. So the discovery of the disease and the medicine, which is called the germ theory, the discovery of medicine definitely has influenced exponential growth. I would say we're going to focus a lot on this, okay? Obviously, without food, you can't grow. I mean, that's a necessary resource. Without stability in a home, it's difficult to expand populations, but the germ theory really did it. All right, I'm going to stop.